See, you hear me? Okay. Volume is up. Okay, good. Okay, so today we're going to start chapter 2 in AP1. We're going to take a look at chemistry, and it's not going to be a full-blown session on chemistry with all sorts of reactions and things like that. We're going to go through chemistry, how it affects the human body, because we have a wide array of chemical reactions that have to take place all the time for us to live. The process of digesting food and breaking it down so we can absorb it is a chemical reaction. The process of breathing is driven by a chemical reaction. When our cells break down sugar, glucose, that's a chemical reaction, and we release a gas called carbon dioxide. You've all heard of carbon dioxide, right? You know, that's what we breathe out. The reason that we breathe faster when we exercise is because we burn more sugar. More sugar, you know, the more demand we place on our muscles, the more sugar that we burn, and the more carbon dioxide that we make. Now, why does that make us breathe faster? Because that carbon dioxide will go into our plasma, the fluid part of our blood, and be converted to carbonic acid. And our brain monitors the acid levels in our blood. It's a chemical reaction there, producing carbonic acid. Our brain says, okay, if we are getting too acidic, we need to get rid of the carbon dioxide. So we breathe faster at exercise to blow off the carbon dioxide. It's just convenient that we get more oxygen out of it, but that's not the driver. We don't breathe faster to get more oxygen. We breathe faster to get rid of the carbon dioxide. Chemical reactions, they happen all the time. Even muscle contractions are a chemical reaction. Everything we do is based on a chemical reaction. So I'm trying real hard to make it sound interesting, but we'll see. So any questions on anything that we talked about last week, or any of the handouts or anything about the class before we go on? Okay, then I'm going to open this up and hopefully bring this up. And okay, it worked. Okay. To understand chemistry, we have to understand a little bit about matter and energy, because we're all about getting energy and using energy in our bodies. Matter, as you see there, is anything that has mass and takes up space. The microscope is matter. The camera is matter. The table is matter. We are made up of matter. So we have mass and we take up space. Now, weight is different from mass. Weight is mass plus the force of gravity. If you weigh 170 pounds, for example, or 110 pounds, or whatever you weigh, you have a mass of 110 pounds. Now, in space, you may be, if you were in the space station, you'd have no gravity pulling on you, so you'd have no weight, you'd be weightless, term we've all heard before. But you would still have the mass. You would still be 110 pounds or 180 pounds or 100 pounds. You would still have that mass. So just because the gravity's gone doesn't mean that the mass is gone. So gravity and weight and mass are two different things, only because of the force of gravity. Now, what about matter? Three forms of matter: solids, liquids, and gases. We have a solid with a definite shape. This little ball here has a definite shape to it. It is a solid. It has a definite shape. It's a definite volume. I can weigh it if I wanted to, but I don't have any desire to. But it will, it has a definite shape to it. Your coffee cup, your pen, your Starbucks cup, they all have, and your Starbucks cup, they all have definite shapes here. Liquids are different. Liquids have a variable shape. The coffee in our cup right now it's contained inside the cup. If you knock it over, then it's going to spread out flat. Obviously, we don't want that because nobody likes to see coffee being spilled, right? Yeah. It's almost a crime to knock over coffee. But liquid has a volume. I can take this beaker and fill it up with water, and I have a liter of water in here. And it has the shape of the beaker, but if I pour it out, it'll spread out flat and find its own shape wherever it has to go. So water has a known volume. We can measure fluids. We can measure the fluid in our blood. We know how much fluid makes up our blood. Our blood is 55% salt water. So we have a definite volume, but the shape of the fluid moves all around. And gases are the exception to everything. A gas has a very changeable shape. Gases move all around, and the volume can change. We could suck all the air out of this classroom and compress it and put it into a high pressure tank about that big. Everything we filled up in here, we could change its volume and change its shape. And if we compress it hard enough, it would liquefy and become very, very cold. Who hasn't been by the hospital somewhere, and in the back of the hospital, there's a big, usually a large tank outside that has what looks like steam coming off of it. It's covered in ice. It's liquid oxygen. It's the oxygen supply for the local hospital. Liquid oxygen. We can liquefy oxygen. We can liquefy hydrogen and nitrogen. When I was in grad school, we used to use specimens preserved in liquid nitrogen. It was minus 300 degrees. You could take, when we got bored, we would take marshmallows and tie them on strings and drop them down into the liquid nitrogen. We'd have a frozen marshmallow and a frozen string too. At 300 degrees, you can freeze just about anything. You certainly didn't go diving for it with your fingers if you dropped it. So anyway, so matter has three forms, and matter goes from solid to a liquid to a gas. Ice melts into water, and then it evaporates as a gas. So it changes all the time. If we eat something, if you eat an apple, you will ultimately convert that apple from the solid, which is going to be mostly carbohydrates inside of it, plus the fiber from the outside. You're ultimately going to convert that into energy, carbon dioxide, and water. Usually when the end result of most things that we eat are going to be carbon dioxide and water. So, okay. Energy is different. Matter can be broken down. Matter can be destroyed. You can burn something. You can eat something. You can let water evaporate. It's going to go away. But energy doesn't go away. Energy is what we use to make things happen. Energy doesn't have any mass to it. There's no way to measure there's no solid way to measure energy. We measure it in voltage. We measure it in calories. If you look at a bottle of Coke or a Snickers bar, it says how many calories are in there. 240 calories in a Coke. I think 180 or 160 in a Snickers bar, depending on the size. That's a measure of the energy stored in that food item. You have a fire pit, and you throw a log on the fire pit and burn the log. The amount of heat and light coming off of the burning log is measurable. It's a measured amount of energy coming off of that log. Energy does work for us. We use energy so we can get things done. And we use energy all the time, but we never destroy energy. Energy can be used, energy can be transformed, but energy can't be destroyed. It just changes from one form to another, and eventually moves into a form that we can't use anymore, and that's usually heat. When we eat a Snickers bar, for example, and our bodies break down the sugars in the Snickers bar, and we get the 160 calories or whatever it is. We get the calories from the Snickers bar, and we use that in our bodies to do things, power our muscles or pump our blood or breathe. Ultimately, a large amount of that energy from that Snickers bar is lost as heat. We don't destroy it, we just don't use it. So we radiate a lot of heat. The reason we have a constant body temperature is because our muscles, which are using most of the energy we consume, can only take about 40% of that. So at 160 calories in that Snickers bar, 40% of that goes to the muscles to work. The rest of it gets released as heat. So we stay at 98.6 all the time because of this. We radiate a lot of heat. Now that heat is not useful to us. It doesn't, once we release energy as heat, it's gone. I mean, it's there. I mean, it still exists. It just spreads out in a form that you can't use. Consider a fire pit. You have a nice fire going in the fire pit. It's a cold evening. You're sitting outside in the fire pit. It feels good. You're about 3 feet from the fire. It feels pretty good. Okay, the heat's radiating out and you're comfortable. You step back about 10 feet. Can't feel the heat anymore. The heat has, the effect of the heat energy has spread out so rapidly in that short distance that you're no longer feeling it. It's like a fireplace. You walk into a room with a fireplace and you go up to the fire like that feels really good. Hopefully the fire's on to do that. So nobody stares at you. But if the fire's going and you feel good, but then you step back and you get far enough away, you don't feel it anymore. Or you come up to it, you're cold, and you warm up, and then you turn around because your backside's not getting any benefit from the fireplace. In that short distance, the heat energy has spread out so far that it has no effect anymore. It's still there. It's spreading out into space, but we can't gain anything by it. So anyway, this is an example here. This is what's called Newton's cradle. And we've all seen these somewhere at some point. And what we're doing is simply seeing the transfer of energy back and forth between the ball bearing on each end. The one on the left hits the other three, and it transfers mechanical energy to the one on the right, and it bounces out and comes back and does it again. And this will happen until friction in the air overcomes the energy being transferred to the ball bearings, and then it'll stop. And that, unfortunately, just like we have to lubricate our bodies all the time because our bodies hate friction, everything hates friction. Energy has two forms. We use them all the time, even if we don't think about it. We have kinetic energy and we have potential energy. Kinetic energy is energy in action. Potential energy is stored energy. If you have a cell phone, you have potential energy in your battery. We charge our phone at night, usually. Plug it into the charger and it's charged the next day, and we run all day with it, and we have to charge it up again. We don't use all the energy in the battery at once. That would be really exciting and probably not very good for your cell phone. So we draw on it. We have lots of stored energy. It says, you're at 89%, or see, in fact, I'll just see what I am with mine. I am at 64%. I've been busy today already. So 64% of stored energy is available. And as I use that up, I'm converting that stored energy into kinetic energy, the energy of going things. The energy in your gas tank, your fuel tank, the gasoline or the diesel represents, you have a full tank. That's potential energy. You certainly don't dump the contents of your gas tank into your engine all at once to get here. I don't think anyway. So we use our fuel. What's in the fuel tank represents stored energy. We convert it to mechanical energy into heat energy, power our vehicle, but we don't use all of it. We can go back and forth between kinetic energy and potential energy all the time. I have a very quick demonstration. Work here. This should do it. Okay. Spent a lot of money on these high-tech objects. This ball is full of compressed rubber. We've all seen them. They bounce. Right now, by picking it up off the table, it has potential energy. When I drop it, it's going to be in motion. That's going to be kinetic energy, and it's going to bounce back up. Now, on the upside, it's running it's storing energy up again, so it can drop back down. So right now it has potential, kinetic energy. If it wasn't storing energy when it hit, it would just lay there. But it has the potential energy to bounce back up and reload, doing it again and again. So this simple little ball will go between kinetic and potential all the time, just like a match. This match, again, we spared no expense in these demonstrations. So, potential energy in the match head. Okay, series of chemicals here in the match head. They react with the chemicals on the strip. These are what they call strike on box matches, as opposed to the kind that strike anywhere. So the chemicals in here in the match head combine with the chemicals on the strip, and they ignite. Right now, it's potential energy. The wooden stick is potential energy. When I light it, match head flares, and I burn the wood. I'm releasing heat and light, as well as carbon dioxide, and a lot of heat and light's energy, and I'm releasing carbon dioxide and some trace gases here too. And so now I can put all my other stored energy matches away. So I've released heat and I've released light. I've converted the chemical energy in the match head and in the wood to kinetic energy. Now let's go back to this. Okay. Okay, now. Okay. So we can release energy. We do it all the time. You eat something, you release the energy in there. The calories in food, the calories on a food label tell us how much energy is in that food. And how much of that are we going to get to use? Well, about 40% of it. Our bodies can grab about 40% of the energy in the calories that we consume to do things. The other 60% goes off as heat. That's just the way our bodies work. Actually, 40% efficiency is not bad at all when you consider, the efficiency of our cars or power plants or things like that. Yeah. Another example here on this animation, you can difference between kinetic and potential energy. Oops, come on, there we go. Okay, so no sound on this. So kinetic energy and potential energy, the bow and the arrow has no energy in it right now. Drawing the bowstring back at some point, will put potential energy into the bow and also transfer it to the arrow. And then when the arrow is released and hits the target, you'll notice that the arrow glowed red in the illustration because the arrow goes through a lot of friction. You could actually measure the amount of heat gain as the arrow is pushing the air molecules out of the way. There's also a release of heat into the target. Every time we go from one form of energy to another, we are going to release heat, and that heat's going to be lost to us. So we will eat the Snickers bar and we release heat. So we convert that chemical energy into chemical energy in our bodies. We store some of that sugar. the arrow hitting the target, the heat energy of the arrow is transferred to the bullseye. And of course, I could hit the bullseye every time I was standing 3 feet away like he is. The point, though, is that we're moving back and forth. And we see transfer here. This, I'll demonstrate it. These are the kinetic energy modes. Just to show you how heavy they are. They weigh, these little balls weigh about 1 pound each. And I'm not going to throw them at anybody, you know. So let me get over here again. Now I need a volunteer to come up and hold this piece of paper. Thank you. I want you to hold it just like this. Another high-tech demonstration. Okay. This isn't going to hurt. Okay. Now I'm going to take these 2 balls. I'm going to slam them together on the paper. And as soon as I do that, there's going to be a hole. But I want you to sniff the area around the hole and tell me what you smell. Okay. It won't hurt. Now go ahead. Take a sniff. Trust me. You smell it already? Burning paper? Really? Oh, okay. So. Does anybody have a sense of smell that's working today? Okay, thank you. Let me do it. I'll let you. Thank you for holding it. Sounds like it's burning, yes. And if you look at the edges, I want to pass this around. Look at the edges, and you'll see it's charred. Because I've taken the mechanical energy of these ball bearings. These are just ball bearings used in industry. Taking the kinetic energy that I applied to these balls, and I slammed them together, and that was converted to heat energy. It actually burned a hole in the paper when I slammed them together. So now we'll never get that energy back. It's spread out, but it works. It works every time. I've been waiting for 2 years to do that, so because I couldn't do it at home when we were teaching, when I was doing this. So, okay, now let's go back to this guy. What we're seeing here is that the archer, if you will, eats food. The energy in the food is converted to chemical energy, which then is applied to the muscles, which then is converted to mechanical energy to pull the bowstring back. And that mechanical energy is transferred to more mechanical energy to get the arrow to go. And then we have mechanical energy from the impact on the target, as well as the transfer of heat energy. Every time we go from one form of energy to another, we lose part of that energy as heat. We don't destroy it. It just doesn't become useful. Have you ever had your laptop running and it gets hot? You're releasing a lot of energy from the battery and it gets warm. Or your phone. Who hasn't felt their phone warm back here where you're using the battery a lot? We're releasing that energy. Some of that energy that's stored in the battery is coming out as heat. So, and we see this all the time. Our cars have some sort of cooling mechanism. Some cars are air cooled, not many, but some are. Most cars have a radiator with a water jacket around the engine to take away the heat. Otherwise, that heat would destroy the engine. That's why we have a radiator. So, okay. Been to Dollywood? Ride one of the rides? There's another good example of kinetic and potential energy. You get on the ride and go up that first hill, and you get to the top of the first hill and you realize that this probably wasn't such a good idea after all, because you just know you're going to go flying out of the coaster, or you're on the Eagle and you're upside down, like this really was not a good idea at all. Anyway, you use a lot of potential energy to get up that first hill. You're storing energy in the coaster. And then as soon as you go down the other side, you accelerate to 80 miles an hour through the release of kinetic energy. At the same time, though, you are experiencing, you're not aware of it, but you are experiencing friction from the air rushing past you, And the wheels on the cart have friction from the on the track. And so we go through a stage of kinetic and potential energy the whole time, because those carts don't have any motor in them. They depend totally on gravity, and they will eventually stop or slow down enough to use a brake of some sort at the end of the ride. So again, it's kinetic and potential energy all the time. Everything in our bodies is based on kinetic energy and potential energy. So what kind of energy do we deal with? Well, we have chemical energy, things that we eat, things that we make. If we store sugar in our bodies, in our liver, in a form of a carbohydrate, a sugar, if you will, we store it as glycogen. Don't worry about that now. You'll hear more about that later. Glycogen is a complex carbohydrate. It's like starch in a potato. We don't store starch in our bodies, but we store a complex carbohydrate. It's human equivalent of starch. That's our stored energy. That's our energy reserve. We also store energy in fat. In fact, there's more energy in a gram of fat than there is in a gram of sugar. 4 calories per gram of sugar, 10 calories per gram of carbohydrates. Our body, of fat. Our bodies like fat for the energy source. So we store energy. That's our potential energy stored up in our muscles and in our liver. Electrical energy, our bodies are electrical. We have a charge throughout our body. Our muscle cells are charged at minus 90 millivolts. Our nerve cells operate about minus 70 millivolts. So we are most definitely electrical. We send nerve impulses all the time, back and forth. We control our muscles with nerve impulses. We control our thoughts, hopefully, with nerve impulses. We send signals from receptors to the brain to say, hey, I'm hot, I'm cold, I'm thirsty, I'm hungry, whatever, with nerve impulses. That's all electrical. Theoretically, if you stuck a voltmeter into your skin, you could measure the charge on the cells. Mechanical energy, we move all the time. We pump blood, we breathe, we walk, we talk. We contract muscles everywhere. That's mechanical energy. But it's driven by chemical energy and electrical energy, but it's still mechanical energy. And we deal with radiant energy and electromagnetic energy. We give off heat, but we also can see. Our eyeballs respond to visible light. We can see things. We can see colors and shapes and images, clocks and projectors and words. Our eyeballs collect all that. That's all they do. They take that visible light is part of the electromagnetic spectrum. It's somewhere tucked in there between radio waves and X-rays, but it's the electromagnetic spectrum that we can see. So visible light shows up, goes into our eyeballs. It's bouncing off of every object. You can look at this model here and see the red muscles here at the shoulder. We know they're red, not because our eyeballs tell us they're red, but because our brain interprets the signals coming off of this that are going into our eyes as red. Because our eyeballs have no clue. Have no clue as to what anything is. They just collect the information. Your phone, you take a picture with your phone, it doesn't know what it's taking a picture of. We have to interpret that picture. The camera has to just collect it. The phone may interpret and say where it is or what time it was or something like that. And then we look at it and say, oh, I remember that one. Yeah, but the camera didn't. The other, I should have mentioned this too, mechanical energy. Hearing is mechanical. Vibrations in the air go into our ear and cause our eardrum to vibrate. And we transfer those vibrations to our inner ear, which activates our auditory nerve, which sends impulses into our brain so we can tell what we're hearing. Sounds make sense, not because our ear can tell you what they are, but at least it sends signals to our brain as what words mean. So we deal with these types of energy constantly. And as I said earlier, we convert energy all the time, but every time we convert it from one form to another, we are going to lose some of it as heat. And it isn't really lost, it's just no longer useful. Think of the fireplace again. Every time our muscles do something, 60% of the energy involved in moving our muscles is heat energy. And nothing we can't recover that. Right? So that's matter and energy. Matter can be destroyed. Matter can be converted to different forms. We can take a solid and burn it. We can take ice and melt it. We can take water and freeze it. We can take oxygen and compress it into a tank and compress it even more into a solid in here. Now, all of these structures, all matter is made up of elements. The elements, an element is something that can't be broken down. An element can't be made into something simpler. Like water can be broken down to hydrogen and oxygen. Table salt can be sodium and chloride, but you can't take sodium and make it something simpler. You can't take an element, the sodium element can't be broken down into anything else except its atoms. And the atoms are going to have the same properties as the element. So you can't break down elements. Gold can't be broken down any simpler. Silver, cadmium, copper, nickel, iron, hydrogen, they all are going to be the simplest version of that substance, and that's what an element is. Now, in our bodies, we only have 4 elements to make up most of our bodies. 96% of us is made up of just carbon, oxygen, hydrogen, and nitrogen. And 70% of our bodies is water. So, hydrogen and oxygen make up water. So, we're 70% water. So there's a whole lot of carbon, a whole lot of hydrogen and oxygen. The remaining 4% comes in from 9 other elements like iron for hemoglobin to carry oxygen, and calcium in our bones, and phosphorus in our bones, for example, and iodine in our thyroid gland, things like that. So we have, most of our body is made up of these 4 simple elements, and then we throw in a few smaller ones to get us up to 100%. This is what's known as the periodic table. We have one up here in the wall, and the periodic table lists all the known elements, and this goes up to 111 elements, and it's probably out of date. I think there's more than that now, because you can actually artificially create elements. I know that Oak Ridge has done that. But the elements that show up in our human body are highlighted here in green on the periodic table. Hydrogen, carbon, nitrogen, oxygen, sodium, magnesium, potassium, calcium. These represent phosphorus, sulfur, and chlorine. These represent the elements that are in our bodies. The big 4, hydrogen, carbon, nitrogen, and oxygen. And everything else, the sodium and magnesium and chlorine and phosphorus and sulfur and potassium and calcium are in much smaller amounts. Now, I will tell you that it's very unusual for someone to ask you, so how many atoms, what's the makeup of carbon? Or What's the makeup of potassium? In a healthcare setting, that's unlikely to ever happen. You know, I know that they don't let the natural science faculty out much, but we certainly don't sit around talking about atoms and elements and stuff like that. So, but it is important to understand the role that they play in our bodies. How do they work with each other? Because nothing operates in a vacuum in the human body. Everything is interconnected. Each organ system cannot stand alone. The lungs cannot stand alone. The lungs depend on bringing air into the body so our blood can have oxygen take to the cells and pick up carbon dioxide and bring that out. And the heart has to pump that to move it around. And that's just dealing with oxygen. That's not dealing with nutrients. So every organ system works together. All of the elements work together in our bodies. Now, elements are made up of, even though they can't be divided down into something less than they are. As I said, you can't take a sample of gold and break it down into something less than gold. All elements are made up of atoms. Every element is made up of an atom, of atoms. And an atom of gold, or an atom of carbon, or an atom of hydrogen has the same properties as a larger substance. A block of gold, a block of pure gold, the atoms have the same property as that block of gold. It melts, it has the same luster, it'll melt at the same temperature. There is no difference other than the fact that you have lots and lots of little atoms or one big block of it. They all have the properties of the element, and the shape, the organization of the atoms determines the property of the element itself. So, because every atom is made up of the same subatomic particles. They're all made of protons and neutrons and electrons. And a proton is a proton no matter which atom it's in. But it's the organization of and the number of protons and neutrons and electrons that make every element different. So first of all, how do we know what these substances are? Well, there's something called the atomic symbol, and that is a letter. And that letter usually shows up, or two, it's one letter or two letters. It shows up in the periodic table telling you what it is. Like O is oxygen. That's easy. C is carbon. N is nitrogen. He is helium. So some of them make pretty good sense, and some we're clueless on. Na is sodium, because the old Latin term for sodium was natrium. And K is potassium, because the old Latin term for potassium was kalium. And those symbols stuck. Cu is copper. Cd is cadmium. Let's see. Ag is silver. Au, directly underneath it on the periodic table, is gold. Instead of having a G or an S, they have Au and Ag. So some of them make sense and some of them don't. But this is how we can tell. Now, the ones that we're going to use all the time, H and O for hydrogen and oxygen, Na and Cl for sodium and chlorine, N for nitrogen, C for carbon. Those are the ones we're going to use. We're not going to pay a whole lot of attention to cadmium or copper or things like that. We're going to probably deal with potassium and sodium and chlorine. Chlorine not so much, but deal a lot with carbon and hydrogen and oxygen. If you're an atom, you are made up of subatomic particles. Your protons. Protons are always positive. They have a positive charge. Every proton in every atom is identical with every other proton. There's nothing different about a proton. They all have a positive charge, and they have a mass unit of 1. This is an arbitrary made-up number by International Union of physicists and physicists and something or other, and chemists. But they've assigned, a long time ago, this mass unit was assigned to protons. They have a mass unit of 1. So they have a positive charge and a mass unit of 1. A neutron has no charge. It has a mass unit of 1 also. Now, protons and neutrons are found in the nucleus of the atom. The nucleus of the atom is what we find, an atom would look something here. If this is an atom, here in the nucleus of the atom, we would have the protons and the neutrons. Protons are positive, neutrons are neutral. And this is the nucleus, the center of the atom. Now, all the weight of the atom comes from the protons and neutrons. So each one of those contributes 1 atomic mass unit. Electrons have a negative charge and have no mass, but they balance out the protons. Electrons in a stable atom balance out the electrons. So they are just as important. The electrons usually tend to orbit. There's an electron. There's an electron. Electrons here, here. And they are negative. They will balance the proton. For every proton in an atom, you're going to have an electron. If there's 6 protons in the atom, you're going to have 6 electrons. If there's 10 protons, you're going to have 10 electrons. Doesn't matter how many neutrons are there. All that matters is that the protons and electrons are balanced. The universe likes to stay balanced. So for every negative charge we've got, we're going to have a positive charge. Protons and electrons balance each other out. It is the mixture, or what gives an atom its unique properties. Why is gold different than lead? Why is carbon different than sodium? It is the combination of protons and neutrons and electrons in the atom. Carbon has 6 protons and 6 electrons. It also has 6 neutrons. Sodium has 11 protons and 11 electrons. So the number of protons and electrons determine the properties, and the neutrons are thrown in there too, determine the properties of each individual atom. Carbon is different from sodium because carbon has less protons, neutrons, and electrons than sodium does. Sodium is different than hydrogen because hydrogen has even fewer protons and neutrons and electrons than sodium does. So we have different atoms have different properties based on the number of protons and neutrons and electrons. Even though a proton is a proton is a proton, every proton's the same, every electron's the same, every neutron is the same. It's what you throw together. It's how you mix it together. Hydrogen, simplest of all elements. And a hydrogen atom has 1 proton and 1 electron. Helium has 2 protons, 2 neutrons, and 2 electrons. The reason that helium balloons float, by the way, is that because if you add up the mass of a helium atom, you have 2 neutrons and 2 protons. That gives you 4 mass units. That's less than atmospheric air. Atmospheric air consists of hydrogen and oxygen. Nitrogen and oxygen. Nitrogen has 7 protons, and oxygen has 8 protons. That's at least 15 atomic mass units as opposed to the 4 from helium. Helium floats, helium balloons float because the mass of the helium atom is much less than the air around it. Because if you blow up a balloon, if you blow up the balloon and toss it out, it's going to bounce around, it's going to drop. A helium balloon floats because the helium balloon, the gas in the helium balloon, has a whole lot less mass than the air around. That's why it floats. Okay, totally irrelevant to anything else. So now what can we tell about an atom just by looking at the periodic table? Well, there's a whole lot here. We have the atomic number, the mass number, isotopes, and its weight. So if we look at our chart, which you can't see because the screen's in the way, the atomic number. The atomic number, if you can see somewhere, you can see it over here. There's a big red number on top of the periodic, on top of each symbol. A big red number, like helium, has a 2 above it. Helium, with the 2 there, tells you that's how many protons are there. How many protons do you have in helium? 2. That's in a helium atom, you're going to have 2 protons. So that's the first thing to tell. The second thing that we see is underneath it, we see at the very bottom, we see the weight in a black number underneath the symbol. Like helium has a big red 2 on top, 2 protons. Its weight is 4. That means it's got 2 neutrons. Because each proton has an atomic mass unit of 1. Each neutron has a mass unit of 1. If we have 2 protons, which it says so in a big red number there, and our weight is 4, then the other two mass units making up the weight came from the neutrons. Trust me. 2 protons, 2 neutrons. Hydrogen has a 1. You can see it here, but it has a 1 above the H. 1 proton. Its atomic weight is 1, doesn't have any neutrons. So what you can tell by looking at these symbols here, first of all, the red number is very important. The number on top of the symbol, if it says 6, it has 6 protons. How many electrons does it have? 6, thank you. 6 protons and 6 electrons, because electrons and protons are balanced. If you got 6 protons, you got 6 electrons. If you got 7 protons, you got 7 electrons. If you got 2 protons, you got 2 electrons. They don't do anything for the weight, but they balance they're more important because they balance the protons. If you look at the number at the bottom, it tells you the weight. Since electrons don't count for weight, whatever, if you subtract that bottom number from the number of protons, that tells you how many neutrons you have. If you take 4 and subtract out 2, that gives you 2 neutrons. If you look at carbon, carbon has an atomic number of 6. It's got 6 protons and 6 electrons. The weight underneath it says 12. That's the most common form of carbon we have, carbon 12. So if we take 12 and subtract out the atomic number, that means that the other 6 must be neutrons. It turns out that carbon has 6 protons and 6 neutrons. That's how we get 12. So just by looking at the periodic table, you can tell right away how many protons you have, how many electrons you have, and how many neutrons you have. And it's the combination of protons, neutrons, and electrons that give you the individual properties. And yet, you would think that, well, carbon is close to nitrogen because carbon has 6 protons and nitrogen has 7, but it is a totally different element. Carbon has totally different properties than nitrogen does. Okay. Atoms. How is an atom organized? Well, an atom looks like a little solar system. In the middle of the atom, we have a nucleus. in the nucleus of the atom, we have the protons and neutrons. And so we have the protons and the neutrons, and we have the electrons in orbit around the nucleus, just like the moon orbits around the Earth, just like the Earth orbits around the sun, just like all the other planets in the solar system orbit around the sun, just like the space station is in orbit around the Earth. It spins around far enough away so it doesn't get sucked in by gravity into the Earth. You know, the moon doesn't get sucked in. The moon does move back and forth. The moon's out there 240,000 miles away. Sometimes it gets a little closer, sometimes it gets a little further away. We know that happens because the moon controls the tides on our planet. And if the moon gets too close, we get very high tides. If the moon's further away, we get a lot of lower tides. But the moon stays about 250,000 miles away, far enough away so that it has its own gravitational field, close enough to the Earth so it can't get away from us, far enough that the Earth can't suck it in. So now, there are two models that we use to describe how an atom is built. The planetary model, which is the simplest to understand, so therefore it's considered outdated because it's simple. We'll show you how electrons are moving around the nucleus. The reality is that they don't follow these discrete orbits. And they're moving at the speed of light. So if you were to take a picture of an atom, you would see what's called the orbital model. You would see a fuzzy ball. Let me show you the picture here. Okay. This is a planetary model image right there of helium. It has the nucleus containing two protons and two neutrons, and it has two electrons in orbit around the nucleus, like little moons. That is a stable, balanced atom. It is unreactive. It cannot combine with anything. It will not combine with anything else. Helium is an inert substance. Helium has, you can't combine helium and water, or helium and hydrogen, or helium and carbon. It doesn't work that way. Helium is inert because it's completely balanced. There are only a handful of elements that are completely balanced, and they tend to run down the whole side here. They're what we call the noble gases. You know, they are stable. Helium and neon, you've all heard of neon, drives through pigeon forge. Yeah. Argon and krypton and xenon and radon are all what we call the noble gases. They are unreactive elements because they are completely stable. The planetary model here shows why they're stable. Helium has two protons and two neutrons in its nucleus. It has two electrons in orbit. It has no space for anything else to try and intrude or combine with it. Now that's the planetary model. It is the simplest approach to understanding this kind of stuff. The electron cloud model is down at the bottom. You've got the nucleus of your helium, but the electrons are moving at the speed of light. That's 186,000 miles per second. All we see is a cloud, because by the time you would take a picture of that atom, the element is, we can't comprehend 186,000 miles an hour, and miles a second. We can't even comprehend 186,000 miles an hour. You know, we have a hard time with that kind of value. So it's all we see is a fuzzy ball where the electrons are. They're moving around so rapidly. They're here, they're there, they're all over the place. But I still like to me, that while the cloud model is realistic, the planetary model makes sense to see how where the electrons belong. So here's what some of the atoms that we deal with look like, some of the elements. Hydrogen. We use hydrogen all the time. 1 proton, 1 electron, no neutrons. We have these electrons in orbit. We saw that, the cloud model. Let me go back. The cloud model shows where the electrons were. They're moving around all around the nucleus, even though the planetary model shows them in discrete orbits. They really are. They're moving around in an orbit. They're not going to get any closer, or they're not going to get any further away. They're just moving around real fast. Now, so here we see hydrogen, 1 proton, 1 electron. It has an orbit. Its first orbit has the electron. Helium has 2 protons and 2 neutrons, and its first orbit has 2 electrons. Lithium has 3 protons, 4 neutrons, and 3 electrons. 3 electrons versus 3 protons. This one has a second level of orbit. This has a second orbit. Here we see the first orbit holds 2 electrons. The second orbit has a third one in here. The second orbit has the third electron. Turns out that first orbit around the nucleus can only hold a maximum of 2 electrons. And that makes a lot of difference. Again, it's probably one of those things you'll never hear anybody come up to you and say, "Hey, how about that second shell of lithium? What about that?" But what we do need to understand is how these atoms are built. So, something else here, something that has real relevance to what we're talking about. Isotopes. Isotopes are types of atoms that they are the same element, but they have a different set of they have a different number of neutrons than what most of the atoms do. For example, carbon. Carbon has 6 neutrons. It has 6 protons. It has an atomic weight of 12. However, there can be another version of carbon that has 8 neutrons, and we call that carbon-14. It's radioactive. Isotopes are radioactive because they have extra neutrons that don't really belong there. The mass number is different. Carbon is still carbon, but carbon-14 has extra neutrons. Those extra neutrons make that carbon atom unstable. They make it unstable, and that carbon atom is releasing energy. The energy that holds those extra neutrons there is being released. The carbon atom doesn't want to be unstable, so it starts kicking out energy just so it can eventually kick out its neutrons and get down to its stable form. That energy makes them radioactive. They give out that energy at a set rate. We call them radioisotopes. If we release enough energy from a radioactive atom, it will kick out the neutron. It's making it unstable, and it will eventually give way to a stable version. So that's all well and good. How does that help? How does that apply in healthcare? Well, let me show you here. 3 types of hydrogen. I can get it. Oh, okay. So they're all hydrogen. They all have a proton in the nucleus and 1 electron. The fact that we have none of them have anything but 1 electron. Protium, typical hydrogen, 1 proton, 1 electron. Deuterium, 1 proton, 1 electron, 1 neutron, atomic weight of 2. Tritium, atomic weight of 3, because it has 2 neutrons, a proton, and still 1 electron. Deuterium is when it combines with water, with hydrogen, with oxygen, makes what we call heavy water. And it absorbs neutrons. Now, what's the point of that? Well, we use deuterium in nuclear reactors to help absorb stray neutrons coming off the reactor. Protium is not radioactive. Deuterium is radioactive because of the extra neutron Tritium is even more radioactive because it has 2 neutrons. It doesn't need those neutrons, so it tries to get rid of the energy. Isotopes will always decay. So what do you remember about an isotope? It's an atom with the same atomic number, but a different weight. You know, carbon has 6 protons. It can have 6 neutrons, it can have 7 neutrons, it can have 8 neutrons. It can be carbon 12, carbon 13, or carbon 14. Carbon 14 is radioactive carbon. That's what we use for carbon dating. Now, from a healthcare perspective, we can use these isotopes for various testing. There are a number of tests that can be done on a patient using a radioactive isotope. For example, if a person's thyroid is acting toward sketching, our thyroid depends on the presence of iodine to make thyroid hormone. Our thyroid sits right here in the middle of our neck, shaped like a little butterfly, right about this level here. And it looks like that. It has 2 lobes on either side with a little, what we call the isthmus in the middle, and it absorbs iodine to function. If we administer radioactive iodine, an isotope of iodine has, here we are, 53, the atomic number is 53, so there's 53 electrons and 53 protons, and its weight is 126. So if we have the isotope of that, we're going to have a greater weight. So it's unstable. So you administer iodine to your patient, and they sort of glow in the dark. Well, they don't glow in the dark, but their thyroid will show up on a scan like that. It will show where the iodine is being taken. And if you have that dark spot there, okay, it says, oh, something's not working here. We're not making iodine here. We're not taking up the iodine. So without having to operate, without having to go, as we say, conduct an invasive procedure, this is a non-invasive way to determine what's wrong with the thyroid gland. It's not, there's a lump on the left-hand side that's not working. Now, is it malignant or is it benign? Is it cancerous or is it harmless? In this case, it's harmless. And so a low-level dose of radioactive iodine, which would break down, which will degrade to its stable form in about 24 hours, is used. There's a scan for gallbladder problems that involves the use of a radioactive substance as a tracer. We can use isotopes for all sorts of things like this. We can use it to treat cancers too, because because all radiation is harmful to living cells. We can administer radioactive isotopes to a patient to help destroy cancer cells. We've sort of gotten away from that now because the beam therapy that you see advertised, proton beam therapy and stuff like that, is much more precise than just administering a radioactive dose to someone to kill cells, because radiation kills all cells, doesn't distinguish. Used to be an individual that would have prostate cancer. Prostate's an organ that sets, males, only males have a prostate. The prostate sits directly below the urinary bladder, but it's the serves as the passageway for the urethra before it enters the penis. It also releases a lot of semen during ejaculation. Prostate cancer is probably the number 2 cancer in males. One of the ways to treat it in a fairly non-invasive way is to place little radioactive pellets in the prostate. I mean, it is not as invasive as having the prostate removed. And the pellets will destroy the cancer cells in the prostate. Of course, now, again, that's being replaced by beam therapy, but everything, a lot of techniques still depend on isotopes. They're still being used in testing to determine like the viability of a thyroid gland or another gland that would use, another structure that would use a specific element. And so we pay attention to radioisotopes, because your patient's going to ask you, am I going to get cancer from this isotope? The answer is no. Well, probably. The answer is usually not, because there are no absolutes. But you could say with a qualified no, it's fine, I can make it feel better. The point is that the radiation level drops off to nothing in 24 hours. So, but we get a nice non-invasive technique for evaluating a patient. Our bodies don't like to be operated on, no matter how simple it is. Our bodies don't like that. We don't. It's always a form of trauma, whether it's what we call outpatient surgery or minimally invasive surgery. Our bodies still react to it. Okay. Let's see. Okay. And try, if I get you confused, let me know. This is, not something that I'm sure you all expected when you got into A&P. You're like, we're going to talk about chemistry, in the second week of classes, but we'll get through this fairly quickly. So, okay, an atom will combine with other atoms, because I know it's boring and I'm doing the best I can. Atoms will combine with other atoms to make molecules. Most common molecule, water. Second most common molecule, atmospheric air, O2, the stuff we breathe, made up of 2 atoms of oxygen. Water, hydrogen, oxygen, and hydrogen, H2O. If you combine 2 atoms together, you have a molecule. It can be elemental hydrogen, it can be atmospheric hydrogen, it can be atmospheric nitrogen, which is 2 nitrogens, or 2 hydrogens, or 2 oxygens together. We don't breathe elemental oxygen, the stuff we see up here. We breathe atmospheric oxygen, which is 2 atoms. If we have 2 or more atoms together, it's a molecule. If we have multiple atoms linked together that are different types, we have a compound. Glucose, sugar, has 6 carbons. See it on the screen, 6 carbons, 12 hydrogens, and 6 oxygens. So you got 3 different types of atoms there. 3 different types of atoms combined together to give you a molecule. Now, the properties of the molecule are totally different than the properties of the carbon atom and the hydrogen atom and the oxygen atom. And so we put them together. We have a totally different material. A compound is totally different than its original atoms. So we have molecules and compounds. Frankly, though, we tend to use the term molecule interchangeably, even though it says 2 or more atoms bound together as a molecule. A compound, blah, blah, has different types. We usually just refer to like a molecule. Compound gets sort of lost in the shuffle. We say a molecule of glucose, molecule of water. So we probably won't say anything other than molecules. Now we can take these atoms and put them together and make molecules. We can make large molecules and small molecules. Now what we find is that not everything gets combined the same way. We have mixtures that form where we have, there's 2 types of, let me back up here. There's 2 types of chemical structures. There is a mixture where we physically mix atoms together. And there are the chemical reactions where we make a change to the molecule. Mixtures can be physically separated out. We can take coffee, and if you had a filter that was small enough, you could filter the water out from the coffee molecules, theoretically. I mean, you could do, I don't know why you want to, but you could filter out the creamer, the sugar, the flavoring. You could filter out the water. You'd be able to separate everything out. You know, some of these filters that you use for hiking and backpacking and camping could probably filter out the ingredients of coffee. You can take salt water and filter out the salt. You can and separate the salt and the water. So you can, something that is physically mixed can be physically separated. Solutions are a good example of this. You have solutions and colloids and suspensions. A solution is something clear. It's a mixture. You look at it. You know, you have a glass of iced tea, and in it, the tea is sweet. You've added sugar to it, or sugar's been added to it. You can't look at a glass of sweet tea and a glass of unsweet tea and tell the difference. The sugar is in solution. You can't tell this is sweet tea, this is unsweet tea, and let's just throw it here, and this is half cut. You can't tell which one's sweet until you taste it, or half cut, or no sugar, unsweet. You can't look at a Coke in a glass and tell if it's Coke or Coke Zero or Diet. Do they even make Diet Coke anymore? Okay, Diet Coke or any of the other variations. You can't tell if it's flavored or not just by looking at it. You know, the properties all look the same. But a solution is what we call a homogeneous mixture, where all the particles, all the atoms that are in that solution are mixed together and evenly distributed. Salt water, you can't look at salt water. You know, if I were to mix up a beaker of salt water, it would look clear. It would look like water. You couldn't tell that there's salt in there because all the particles are in solution. Now, a solution, as we say, a solution is made up of what's known as a solvent and a solute. Solvent is the dissolving medium. Usually it's water. We make up tea, and we add sugar to it. We take water and we run it through coffee grinds, and we get brewed coffee. And we added that. You can't look at it and say, well, there's the water, there's the coffee, there's the coffee, there's the. It's evenly distributed. The solute is the substance that gets dissolved. I take a beaker and I add 100 grams of salt to it, table salt, sodium chloride. The salt is the substance being dissolved that will go in solution. The solvent is the water, and I fill this up with water. After I take out the other stuff in here, this is 1 liter in this beaker. If I add water to that, and then add 100 grams of salt, the salt disappears. So salt totally disappears. It's invisible. It is homogeneous. It all looks the same. So the key terms here for a solution: solvent and solute. Solvent is the dissolving medium. Whatever we dissolve, whatever we're dissolving the substance in, usually water. The solute is what's being dissolved. Sodium chloride, probably the #1 thing in our bodies, because our blood plasma is 55. It makes up 55% of our blood, and the blood plasma is salt water. Sugar in our blood sugar is made out of glucose. Glucose is in solution. You eat something with a carbohydrate in it, or you drink something with a carbohydrate in it, a sugar in it, and that goes into our blood, because everything we eat and drink goes into our blood, raises our blood sugar levels. You can't take a sample of blood and take the plasma out of that sample and say, oh, I can see a lot of sugar in there because it's all in solution. So solutions are homogeneous. They're totally transparent. You can see right, doesn't matter what, if they're clear or if they are brown or yellow or pink or whatever, orange, whatever flavoring that's in there, you can still see right through them. So here's a solution right here. Salt added to water goes into solution. I can add 100 grams of salt to a beaker with a liter of water in there. It will go into solution. I can do the same thing with sugar, and it's dissolved in the water. You can't see the sugar, you can't see the salt. It's all evenly distributed. So you have a transparent solution. And so the solute gets dissolved by the solvent. The solute is the solid substance, the solvent is dissolving medium. And it's usually going to be water. Okay. Now, and this is the last thing we'll talk about for today. How do we tell what percent, what is the makeup of a solution? If I were to take my beaker and I put a liter of water in my beaker and I added 100 grams of salt to it, well, a liter of water has 1,000 milliliters. And if I add 100 grams of salt to that, 100 is 10% of, forget the units, 100 is 10% of 1,000. So if I put 100 grams of salt into a liter of water, I would have a 10% salt solution because 100 is 1/10 of 1,000. So I have a 10% salt solution. That's how we, whenever we deal with any kind of chemicals, that's how we make things up. That is the simplest of all solutions. And most of the solutions that we deal with in healthcare are going to be based on percent. Normal saline, 0.9% sodium chloride. Or maybe you're going to have a dextrose solution, a 5% dextrose in water. You're never going to administer distilled water to a patient. It's always going to have salt and maybe something else going in there with it. So 10%, simplest, very simple. 10%, 20%. If I were to make a 40% glucose, a 40% sugar solution, I'd put 400 grams of sugar in here with a liter of water and fill it up to the 1 liter mark. 400 is 40% of 1,000. So it's as simple as that. Second type, milligrams per deciliter. Only a few things we use this for. A deciliter is 1/100th of a liter. A deciliter is 1/100th of a liter. And so we would measure certain substances in our body using this milligrams per deciliter, particularly things like blood sugar. If you've ever had blood work done and your glucose level comes back as 80, 90, 100, or 200, or 300, or 400, your fasting blood sugar, because if you ever go in and have blood work done, you don't eat anything, don't drink anything. Have you ever done that? And so then you get the results back, and they have a whole series of numbers, and it says blood glucose 90. It's fine. Anything under 100 or below is considered a healthy number for blood sugar. The unit that we measure that in is milligrams of sugar per deciliter of plasma. So 1/100th of a liter. And to be perfectly honest, usually in values like that, you're looking at the number. You're not worried about the unit. You're looking at the number. How many red cells do you have in a sample? Well, it's there is a unit for that. A typical blood sample has about 5 million red cells in a I think it's measured in deciliters, I forget, but it's 5 million red cells and about 5,000 white cells. You don't worry about the units. You know what the units are automatically. It's on the chart. You're looking at the numbers. The numbers, what's important. Anyway, and the third type here is called molarity. And you know, it's 12:30, and I'm going to stop because I can't describe this, and I got to get ready for lab anyway. So, I mean, I can describe it. I just can't describe it in 30 seconds. So, we'll pick up with this on Thursday. And anybody have any questions on anything? Yes, that's fine, unless you really want to keep it as a souvenir. Yeah, I thought so. Okay. And I've got everybody on attendance, so don't worry about it. We're good. And I guess I'll see you in lab this afternoon. So, and I want to get us out of here.